everyone. So today we're going to discuss standing waves, and we're just going to sort of review some of the basic facts about them, and then in particular we're going to focus on solving for the various allowed frequencies and wavelengths in different circumstances where you have either waves on a string or in a pipe, and you have various different sorts of boundary conditions in order to enforce. So just reviewing a little bit about standing waves first. So of course these are waves that they oscillate in time, but they do not propagate. Which of course is why they're called standing waves, because as opposed to traveling waves, which do propagate, standing waves sort of don't go anywhere. And they're created by, so you superpose two waves, and they need to have the same amplitude and the same frequency. But they need to be traveling in opposite directions. So each of them you can imagine being a traveling sinusoidal wave, but together they create something new, and the superposed wave is a standing wave. So each travels in opposite directions. So as I briefly mentioned, you could imagine all sorts of different types of standing waves propagating in different types of media. But the two that we'll focus on today are creating standing waves on a string and creating standing sound waves in a pipe. So the name of the game here, in order to solve for the different allowed wavelengths or frequencies, is really enforcing boundary conditions. And really enforcing the particular boundary conditions that we have is going to be enough to be able to solve for the different frequencies and wavelengths that are allowed in the various circumstances. So for strings, there are two types of boundary conditions we'll consider. So we'll consider fixed ends and then what I'll refer to as loose ends. So a fixed end is like when you have your guitar and the two ends of your guitar string are fixed. They're held in a particular location and they aren't allowed to move at all. So fixed ends have zero displacement. So y of, well, I'll just say y equals 0 at the ends, whatever that might be. So y equals 0. And then loose ends, on the other hand, so this you can imagine if you have a string that's attached to a little loop and there's a pole and it's allowed to move up and down the end of the string. So this is sort of a soft boundary as opposed to this hard boundary. In that case, what you find is that the partial derivative of the function describing your wave with respect to x, that has to vanish. So basically what you're seeing is that the slope at the boundary, the slope of the waveform has to vanish. And again, maybe this will become a little clearer when I actually start to draw some pictures. And then the other case we'll consider is sound waves. So sound waves in a pipe in particular. So it's just a one-dimensional sound wave. And again, we'll have two different types. So we'll have closed pipes. So this is just a pipe where one or both of the ends are closed. And in that case, similarly, you have zero displacement. And you can also alternatively have open ends. And that's actually where your change in pressure, so you can, of course, describe sound waves either by the displacement or by the density, so the average displacement of the air molecules, the density of the air in the pipe or the pressure in the pipe. And so with open ends, we'll see that the pressure goes to 0. Now, of course, the pressure is related to the displacement by the derivative. So this is really the same thing as saying that the derivative of the displacement with respect to position goes to 0. So what you notice right away is that these two different types of boundary conditions we have for strings and for sound waves are really identical types of boundary conditions. So now let's draw some pictures. And really by drawing these pictures, you are able to deduce the general form for all allowed frequencies and wavelengths. So let's first consider strings. So if we consider the case where we have fixed ends, well, I guess maybe I'll just start by saying we're going to consider 3 different cases, right? So we have 2 different types of boundary conditions. We always have 2 different ends to consider. So we can apply the different boundary conditions in the various possible combinations. So we could either consider the case where both ends are fixed. We could also consider the case where you have one fixed and one loose end. And then we could consider both loose ends. All right, so what we saw is that, or what we said, is that for strings, if we have fixed ends, then we have 0 displacement. And what that means is that we have a node. So terminology that I have not yet introduced in this video is if you have a displacement node at a particular place, what that means is that is a place where your displacement function goes to 0 at all times. And so what I'm going to do is I'm going to represent a node by a little pink dot like this. So if we have 2 fixed ends, then we must have a node at each end. Now what I'm going to do is I'm going to actually draw a few different examples of solutions given these boundary conditions. So planning ahead, I'll draw 3 different solutions that we could consider. So all you need to do to understand what allowed solutions you have given these boundary conditions is to imagine different types of standing waves that you can draw given sort of these endpoints. And what I mean by that, right, is so the easiest thing we could draw in between where we have both ends fixed is simply something that looks like this. And so what we're really doing, so these are going to look like sine waves or cosine waves. And so what we're doing is we're drawing allowed sine and cosine waves in between the 2 ends. So one might look like this, where we have a half of a wavelength of your sine wave in between the 2 nodes. But then you could also consider the case where you add a node in the middle. So you're allowed to freely add nodes in between, as long as you just keep the nodes at the end. The next thing you could draw is where you have exactly 1 wavelength of your sine wave in between the 2 nodes. And then you could keep going and add 2 more nodes in the middle and have something that looks like this. Oh no, mine are, sorry, they aren't supposed to hit each other like that, but you get the idea. Now, of course, so each of these are drawn for some particular time. And what really is happening with standing waves is, I said, they're oscillating in time, they're just not propagating. So at a half of a period later, what will have happened is this string will have moved all the way down to the bottom. It'll have completely reflected. And that's true in all of these cases. Sorry, these are all mushing into each other. I guess I drew a little too big. So those are going to be your first three allowed harmonics, or your first three allowed wavelengths or frequencies, whatever you want to call it, having two fixed ends like that. So next, if we have one fixed and one loose end, then again, we have, maybe I'll only draw two examples in this case since I was clearly running out of room. We're going to have a node at one end. So again, I guess I should add these little pig dots again are called nodes. So we'll have a node at one end, but if our other end is loose, then what we're going to have is this place where the derivative vanishes. And what that really means is this is where we're going to have something called a pressure antinode. And what I'm going to do is draw that with a sort of a blue dotted line. So this is now an antinode. And this is where our displacement is going to be at its maximum value. And so again, if we draw our allowed waveforms for in between a pressure node, or not pressure, but a displacement node and a displacement antinode, you could draw something like that that's actually a quarter of a wavelength. And then again, at some later time, it will have, so exactly a period and a half later, it will have reflected. And basically what's going to happen in time is this is just going to go up and down like this. But at the node, the displacement must vanish at all times. And then I guess I said I would draw one more example. So again, if we're drawing a node at one end and we have an antinode at the other end, well, what's the next thing we can draw? Well, again, we can add, just as before, we can imagine adding another node in the middle, and then your solution will look something like this. And then again, at a half a period later, it will have reflected. And then finally, rounding it out, if we have two loose ends, then we have antinodes at both ends. I want to make sure, so let's, again, I'll only be able to fit two examples because I sort of ran out of space. But so if we have two antinodes at each end, then we can imagine first the case where we have one node in the middle, and then the case where we have two nodes in the middle. And these will look something like this. Oh, sorry, I guess I should have made, these are at two different times, so I should have made one of these sort of a dotted line again. So I definitely don't want to confuse you. I know a lot of times when people draw these solutions, they sort of just draw the two different time shots, and I think that often confuses people. I really want to make this clear that what I'm drawing on each of these plots are two different times. So if, for instance, the solid curve is what the string looks like at time t equals 0, then the dotted curve would be what it would look like at time t equals the period over 2. So it would be at some later time. So these would be, so the first three harmonics, or the first two harmonics in these cases for strings, and if you wanted to keep drawing them, you could just do that by continuing to add nodes in the middle and find more and more allowed wavelengths and frequencies. So the next thing we could consider are sound waves. So if we have sound waves, so there's actually two common different ways of drawing sound waves, and I want to consider both of them. So we could draw them in terms of the displacement or in terms of the pressure of the sound wave. So these are sort of two different common ways of representing them. And the reason I'm doing that is because So what we saw for our boundary conditions here, so if we could consider a closed end, then this is going to be a displacement node at a closed end. This is where the displacement vanishes, but that turns out to be a pressure antinode. So if I draw the graph instead in terms of pressure, then where we have a node on the displacement plot will be an antinode on the pressure plot, and then vice versa. And the same is going to be true for open boundary conditions, where we see we have a pressure node if we have an open boundary condition, but a displacement antinode. So let's, in the same way, using our same little red dots for nodes and blue lines for antinodes, let's consider closed. So what I mean by that is we'll consider a pipe where both ends are closed. And let's see, maybe I could fit 3 of them in here. So if we have closed boundary conditions, what we said is a closed pipe has a displacement node. So in all of these cases, we're going to have nodes at both ends. And then we can draw, again, what's allowed. And what we'll see is actually it's going to look exactly like the case of the fixed end strings. So in this case, we could add a node in the middle, or we could add 2 nodes, or going on, we would add 3 or 4 or 5 nodes. And we have something that looks like that. But then over here, if we draw this instead in terms of pressure, we can draw the exact same waves at the exact same time shot. But in terms of pressure, if instead we plot the pressure then instead of the displacement, then what we find is we have pressure antinodes. So maybe you can see this. So we have the blue dotted line antinodes. So what we want is we want to draw the sine curves where we have max displacement at the ends. So what that really means is the first one you can do has 1 node in the middle, then 2 nodes, and then 3 nodes. So these solutions will look something like this. Where again, what we're seeing is we're constrained such that we have the pressure at its maximum at the ends. So what I'm going to do now is I'm going to draw so we can consider all of the different various boundary conditions. So we can have closed, open. So what that is a pipe like this. Or we could have closed or open, open. Sorry, that's sloppy. So we have, I'll just and so for the displacement, we always have a node at a closed end and an antinode at an open end. So these are all antinodes on this side and nodes on this side. And then for open, open, we have antinodes on both sides. So what I would like you to do is to pause the video now and finish drawing all of these plots for yourself. In the meantime, I'm going to also draw all the plots so that you can compare your answers with mine. But go ahead and hopefully pause them and draw all of these first 3 sort of allowed harmonics for both the displacement, and I also would like you to draw them for the pressure. So, repeat all of these pictures here and draw the first 3 allowed ones. All right, so hopefully you were able to get all of them. Just filling in these diagrams, again, noting that in the case of sound waves, if you have a displacement node, you have a pressure antinode. So these all should sort of look you have the opposite boundary conditions in each of these. And so now that we have all of these pictures, and maybe we could have drawn more if we wanted to, what we really wanted to figure out is what the allowed frequencies and wavelengths are for these different cases. And you can do that by simply sort of reading it off. So if we take, in all of these, we take one end to be x equals 0, and the other end to be x equals L, which is either the length of the string or the length of the pipe, we can literally just read off what the wavelength is by knowing what one wavelength of a sine wave looks like. So we'll see that in all three of the top cases, it's actually the same. What we have is that the length of the pipe is equal to the wavelength over 2. And that's because exactly 1/2 of a wavelength fits within the length of the pipe. And then the next harmonic, we see that the length of the pipe exactly equals the wavelength. Exactly one wavelength fits. Now this one, it's a little bit maybe harder to see in the pressure ones, but if you think about it for long enough, you could convince yourself that that's what's going on. And then in the third case, what we have is the length equals 3 lambda over 2. And hopefully what you'll start to notice is that there's a pattern here. Basically, we have integer lambda increasing, right? So in general, if we were to continue drawing these, what we would find is that in each case, the length is related to the wavelength by some integer times lambda over 2. And if you aren't convinced of that, maybe just keep drawing where you're fitting to these boundary conditions, and you'll see that in all of these cases, that's what ends up happening. Now it turns out, maybe I'll just skip ahead to these open boundary conditions, that this all looks exactly the same. So the first one is lambda over 2, the second one is lambda, and the third one is 3 lambda over 2. So again, we have the same general expression, which I barely have room for, which is L equals N lambda over 2. Now, it's these mixed boundary conditions that get a little weird. So in this first case, we see that we have 1/4 of a wavelength only. And then the second case, we have 3/4 of a wavelength. And then in the next case, we have 5/4 of a wavelength, so just over a wavelength. And so there's sort of two different ways you can think about this. You could really just think about it only allows odd integers, or you could actually write an odd integer. So let's see. So there's two different ways, right? So we could write this as L equals M lambda. Oh, sorry, this is a 4 over 4. Or we could alternatively write it in terms of 2n minus 1 lambda over 4. So I should, for completeness, I should have said, so this is where n equals 1, 2, dot, 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 all the way up, so equals an integer. And that's the same case down here. So we can again write n as an integer, in which case this would be right. So we're starting with 1, so we see the first one is lambda over 4. Or we could just write it in terms of m, where we say m is an odd integer specifically. Anyway, so there's just a couple different ways you could write those solutions. So some people will say, because you have only odd integers in the case of these mixed boundary conditions, they'll say that only the odd harmonics are allowed, so the second and fourth, all the even harmonics vanish. Or you could write it this way, and then, any n is allowed, so it sort of depends on which way you write it. But anyways, so this is how, by just drawing a bunch of pictures, you can determine the different allowed wavelengths for the different allowed harmonics of standing waves. And then, of course, you can also write this alternatively in terms of the frequency of your wave by simply using the fact that the velocity, so the velocity, in all of these cases is the same because it's the same medium. Similarly, in the sound pipe, it's the same sound, so the velocity is the same. That's equal to the wavelength times the frequency. And so you can solve for f by simply solving for lambda and then plugging that into here. And then you can solve for the allowed frequencies. All right, so hopefully that cleared some things up and showed you how you can solve for the various standing wave solutions for different boundary conditions for standing waves on strings or standing waves in sound waves in a pipe. Thanks.